All right. Hello and welcome to this presentation about the paper titled A Ranking Stability Measure for Quantifying the Robustness of Anomaly Detection Methods. I am Lorenzo from DTI Lab of KU Leuven in Belgium, and I have worked on this paper together with Connor and Vincent from KU Leuven as well. I want to start motivating our work through a simple and visual example. Consider a two-dimensional unlabeled dataset composed of both normal and anomalous examples. What we do here is to apply an unsupervised anomaly detection algorithm in order to rank the full triangle test examples from the least anomalous to the most. But since the degree of anomalousness strictly depends on the training data, does the ranking change when drawing different training sets from the same distribution? By drawing, for instance, a new training set, it may happen that the ranking positions change a lot. Look at the test example 1. Previously, it took the third position in the ranking, and by changing the training data slightly, it is now in the first position. And perturbing the training data for the third time leads to a completely new anomaly ranking. So the goal of our work is to capture these variations in the ranking. We want to provide an answer to this question. How consistent or stable is an anomaly detection model in making anomaly rankings? If, for instance, we drew 5 different training sets and we applied 3 different anomaly detectors, we would obtain, as shown here in the slide, different variations in the ranking positions. But which of these 3 models would you assume to be more robust? Well, probably the last one, since every time the positions remain the same apart from the last 2 test examples. So what we need is a measure of stability which is able to quantify the robustness of any anomaly detection model. And in practice, given the training and test set and an anomaly detector, we want to design a stability measure to quantify the consistency of the model to rank the examples under variation of training set. From a practical perspective, such a measure will make it possible to compare different anomaly detectors and pick the most robust, according to the nature of both the model and the dataset. In fact, assuming that different models are equally accurate, we should trust the ranking of the most robust one, as it is unlikely that the ranking will change if we had observed slightly different training data. So, how can we quantify the robustness of any anomaly detector? Let's first have a look at the standard process of unsupervised anomaly detection. In that case, we assume that we don't have any label information. So first, anomaly detectors assign an anomaly score to each unlabeled example, which represents its degree of anomalousness, where higher scores indicate a higher degree of anomalousness. Second, anomaly detectors sort the anomaly scores and put the anomalies at the top of the ranking. Assuming that the expected proportion of anomalies gamma is given, a threshold on the anomaly scores can be chosen such that the examples with a higher score get the anomaly label, and the examples with a lower score get the normal label. This threshold is set such that the proportion of examples with a higher score corresponds exactly to gamma. And finally, the anomaly detectors predict anomaly if a score is greater than the threshold and normal otherwise. So observe that changing the anomaly ranking would lead to different thresholds and in turn to different predictions. This is why we are interested in stable rankings. Now, our measure for quantifying the robustness of any anomaly detection model can be computed in 3 steps. In the first step, we need to simulate slight changes in the set of available training examples. The issue here is that the true distribution of examples is usually unknown, so that we cannot draw a subset from the actual population. So even though it introduces some bias, we draw many times subset of a random size from the actual and available dataset, and each time we retrain the anomaly detection model and construct the anomaly ranking on a holdout test set. By subsampling the training set, we are in fact simulating perturbations in the training data drawn from the true underlying data distribution, as it represents the case when other examples regarding the same problem would be collected. In the second step, we assign to each test example one stability score, representing the robustness of the anomaly detector in giving the same position to it. Across the iterations, a test example is awarded to different anomaly ranking positions. And in order to remove the dependency to the size of the test set, we normalize the ranking positions between 0 and 1. In this example of 4 test examples, a value of 0.25 is given to position 1, 0.5 to position 2, 0.75 to the third, and finally the last position would go to 1. So, since the example stability quantifies the variation in its normalized ranking positions, the most obvious way to do this is to measure the standard deviation of the normalized ranking positions. The standard deviation can measure the pure variation of positions, regardless of the degree of anomalousness. However, this does not reflect that some changes in the ranking are intuitively more important than others. Whether two normal examples change positions in the ranking is not so important as whether an anomaly suddenly ranks lower than a normal example. In other words, we care mostly about variation in the top part of the ranking that presumably contains the anomaly. To model this, we fit the beta distribution over the set of positions with the mode corresponding to the anomaly threshold, as determined by gamma. Then we can take the area under the plot between the mean and the max position of a test example, and thus an example that has large range of ranking is penalized more when computing its stability. In the last step, we aggregate all the example-wise stability scores by taking the average yielding to the model score, which expresses on average the stability of the anomaly detector. The model score is then normalized by assuming that the worst scenario consists of ranking the test examples randomly. In fact, it makes sense to assume that the model will always rank the examples better than randomly. But let's now pass to the experiments. To empirically prove the effectiveness of our stability measure, we carried out a large set of experiments. The first question that we want to answer is, does our new measure of stability allow cross-comparison among models? In the paper, we ran experiments on 9 standard benchmark datasets. Here we will discuss 3 of them. In the plot, each dot of certain color represents both the stability and the area under the ROC curve achieved on the benchmark dataset by one of the 7 anomaly detectors instantiated with a specific set of hyperparameters. The large dots are the corresponding average per method. You can see that different detectors have varying stabilities and that there is limited correlation between AUC and our stability measure, indicating that our measure captures a fundamentally different aspect of performance. And aggregating all the results for each method and per measure, where we consider stability, AUC, and average precision over the whole benchmark, we can see that there exist models with low AUC and high stability, like one-class SVM, as well as very accurate models with low stability, like iForest. This strengthens the fact that our novel measure captures the different quantity than the classic performance measures. In a second experiment, we gather evidence that the stability measure can effectively capture the robustness of anomaly detectors in making anomaly rankings. To do so, we simply check whether the final stability score when drawing bias subset is certainly lower than when drawing random subsets. An easy strategy is to cluster the full training set and then, by assigning to each of them a weight, draw samples with the given non-uniform weights. So, in this case, instead of capturing the ranking variations under slight perturbation in the training set, we capture the robustness of the model under relevant perturbations. What we expect here is that any model would be less stable when drawing biased subsets. And in fact, results show that uniform sampling returns greater values than the bias strategy independently of the hyperparameter, highlighting that the stability measure behaves as we expect it to. It also does not depend on the dataset at all, as you can see from the slide. To summarize, we proposed a novel stability measure to quantify the robustness of anomaly detectors, which allows cross-comparison among models and behaves very realistically. For any further information, you can have a look at the paper and find the code on my GitHub page. You can also contact us via email, and thank you for your attention.